Alright, so we're going to get started back up with our notes for geometry. This is going to be lesson 5.1. It's on bisectors of triangles. And we're going to be looking at lines and how they form triangles and whether they're perpendicular and what bisector means and how we can use that to figure out the lengths of triangles and the angles of triangles and so on. So here again we're talking about bisector. So bi is 2, right? So really we're dividing something into 2 sections, okay, within a triangle. And the thing to remember is there, there's 2 sections, it's where they're equal to each other. So we're looking for rules where if we know that they're equal to each other and we know what one equals, how can we then use that to figure out what the other one equals? It's really what this whole premise of this lesson is. So what's a segment bisector? So it's any segment, any line, or any plane that intersects a segment at its midpoint. So that means the middle, right? And where that means if it's exactly in the middle, side A equals side B. Okay. And they can be perpendicular, and if they are perpendicular, we call it a perpendicular bisector. But we could have one like this, where we have, line QR bisects line XY, and this could cut, XY in half perfectly, and it doesn't have to be perpendicular, but when it's perpendicular, it's called a perpendicular bisector. When it's not perpendicular, this is at a different angle than 90, it's just called a bisector, a segment bisector. There's some theorems that we should know and remember that will help us solve for unknowns. The first one is the perpendicular bisector theorem. Now we're not going to do proofs with these, but we just need to keep in mind what is the rules to remember when we're talking about a bisector that's perpendicular. So this one says in words, it says if a point is on the perpendicular bisector of a segment, then it is an equidistant from the endpoints of a segment. So here we have this triangle, right? And we have this line CD running through it. We see that it's perpendicular, okay? And we can make some assumptions if this is this perpendicular bisector. And it says this. So if CD is perpendicular to the bisector of AB, right here. So this line is a perpendicular bisector of AB. Then, if that's true, if this is a perpendicular bisector right here, that means AC equals BC. So this equals that. We also know that AD also equals BD as well. We can say that as well. So this is kind of this one, perpendicular bisector theorem. When we know it's perpendicular, it's a bisector, it cuts through this bottom one, and we know that these two are equal as well. And then we can call this an isosceles triangle, right? 2 sides are equal. So let's look at another one. Next one we want to look at is the converse of that. So the converse of the perpendicular bisector theorem. Kind of looking at it the other way. So it says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So here we have this triangle, right? And we see it cutting through here. And we see that these sides are equal, right? And we see that these are equal. So we know that's a bisector. We look at the angle, that means it's 90, and that means it's perpendicular. So then we can make some assumptions about it. And this, we can say this. So if AE equals BE, then E lies on this, and it is the bisector, perpendicular bisector of this. So we know if this line cuts through here, and we know that this side is equal to that, we can then say this point is on CD, and it's a perpendicular bisector. That can be helpful when we're looking at lines and they're cutting across triangles and things like that. So those are the 2. And this one's the converse of the perpendicular bisector. So if we add a few more terms, and then we're going to look at how you apply this. But another term that's important to use for these bisectors and everything is something called a concurrent line. Okay? And this is the condition where three or more lines intersect at a common point. So we have line C, we have line array B, and then we have, not really array, but it's a line, we have line A. And they all intersect at this point P. We would call that point where they all meet the point of concurrency. And these are concurrent lines. Another point we want to look at is circumcenter. So if we have something like a point of concurrency where lines, three or more lines are crossing, we then have something called the circumcenter. Okay? So a circumcenter is talking about the point of concurrency for the perpendicular bisectors of a triangle. So if we then do these, we draw three lines on this triangle, and the spot where they meet, we can call that the circumcenter for the triangle. And the thing to remember, it can be on the interior of the triangle, it can be on the exterior outside, or it can even be on the side of one of the triangles. And here, that one's right here. We call this the circumcenter. So we have three lines, this one, and this one, and we make bisectors, right? So this is a perpendicular bisector. So if we take this line, we cut this leg in half by drawing a perpendicular line. And then we take this segment, this leg right here, the hypotenuse, we cut it in half, make it 90 degrees, a perpendicular. And then we do this one, and we do it, make it perpendicular. It cuts this side exactly in half. It's a segment bisector. And then we know the point that those lines meet, we call that the circumcenter. And there's a theorem that goes along with that. The circumcenter theorem, this says the perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. So we got a vertices, and a vertices. So then we know if we have this, it's an equidistant from here, and from here. Okay? It's really helpful to figure out measurements out on a triangle. So keep that in mind, that circumcenter theorem. Just want to cover a few more, and then we'll do some practice problems, a few more words. So here we have angle bisectors. So before we had segment bisectors, which were like lines. Now we're talking about angles. So if a bisector cuts in two, here we're talking now about an angle getting cut into and getting cut into perfectly. So an angle bisector divides an angle into two congruent angles. They're the same, right? So that means angle A is congruent with angle B. Okay, and this, whatever's doing that, whatever's the angle bisector, it can be a line, it can be a segment, or it can be a ray. That doesn't really matter. What the thing we're really worried about is it's cutting it in two perfectly, where each angle side of that bisector, each angle is equal to the other, is congruent with it. Okay, there's some theorems that go along with that too, and these are kind of primary or rudimentary, so keep these in mind and we'll be building off of these. So the angle bisector theorem is the first one. It says if a point is on the bisector of an angle, then it is an equidistant from, or distance, it is equidistant or an equal distance from the sides of the angle. So if we have this angle right here, we have B, and if we had an angle out here, we could call this G, and we had another one here, we would have H. So if we had this thing formed, okay, and then we had some points along this line D and E, okay, and we had this bisector, this angle bisector going through it, and it had point F on it, okay, we could then say if this angle is equal to this angle, right, let's ignore that line, this angle and this angle are the same, so then we can tell, but if we look at that, we can see that this is an angle bisector. And then we could then say, if we put a point on this line, and then we draw perpendicular lines from this side of the angle, and from this side of the angle, we could say, and we make sure that they're perpendicular. They can't be like this way or this way. It has to be the shortest possible line, that perpendicular line, the shortest perpendicular line, or line from there. We can say that these are equal to each other. If we want to say it in more mathematical terms, we can say if BF bisects angle DBE, right there, if this one, BF, bisects it, and FD, right here, is perpendicular to BD, it has to be, and then FE, right here, is perpendicular to BE, right here, then DF, this new line and this line here, FE, they're equal to each other. They're the same distance. Okay? That's the angle bisector theorem. And then we have this last one. This is the converse angle bisector, the converse of it. And this says if a point in the interior of an angle is equidistant from the sides of the angle, then it is on the bisector of an angle. So keep that one in mind as well. So then if we have an angle, let's draw this. We have a bisector going, that's not very good. We'll pretend it's a bisector. Okay, just pretend with me here for a little bit. Alright, so I actually redrew this one here, and to make it a little bit better. So if we have this angle here, and we have this angle formed, and we have this bisector AB cutting through it, cutting this angle in, making them the same, and we have this point B on here, we could say that it's the equal distance from a perpendicular line from this and a perpendicular line from that. So then we would say this is equal to that. And if we had this labeled as a point, we could say F and G. We could then say GB is equal to BF. And those are that's the last theorem I wanted to show you. I'm now going to show you a few problems, and then we'll move on and be done with the notes. And these are pretty basic. I just want to show them to you. So this is the example 1. This is use of the perpendicular bisector theorem. And this one says find the measure of AB. So we got this triangle here, right? And we have this line CA running through it. There's a point A and a point C, we could say, where they cross. And these vertices B, D, and A could also be vertices. And we have all this out, and we know this is a bisector because this side is equal to that, and it gives us this right triangle. So if all that's true, and we know that AD is equal to 4.1, this side should be equal to this side. So then it says find the measure of AB. So if we know this side, AB, is equal to AD, we can just say AB segment is equal to AD, and since AD is 4.1, AB is 4.1. Pretty straightforward. Okay. And you kind of see that down here. This perpendicular bisector, AB equals AD, AB equals 4.1. So let's look at the next one. Same kind of deal. We have this right here. So we have this condition where we have a Y, looks like a Y and a W and a Z. So we have this triangle. We have this line cutting through it, and we also see that these sides, so side WY is equal to 9, and then we know side YZ is equal to 9. So we know these sides are equal. This is perpendicular, so that tells us this is a perpendicular bisector. So that means if this whatever WY is equal to what YZ is. So then if we know YZ is 3, we then know WY is 3. So we just use that logic. WY is equal to YZ, so whatever this is equal to that. If YZ is then equal to 3, we'll put these on here. And then WY is equal to 3 because of this. And all the other things we can read. And then we have one last example to look with this one. If we then say this thing right here, so we have this triangle right here, and this one wants us to figure out what is the length of RT right here, right? So then if we look at this, we have some kind of bisector. It's perpendicular, right? And then we know it is a bisector because we're thinking maybe it's a bisector, but it is perpendicular. Then we look at the sides, and these lines tell us they are the same. So if these are the same, it cuts this in half. These are the same, these are the same. So then we can say that RT is equal to QR or RQ, however you want to say it. Probably be better to say RT is equal to RQ. We write that. Not sure it matters. So then we can make whatever they are equal to each other. And we have 4x minus 7 right there. RT is equal to 2x plus 3. We then do some math. We're going to minus 2x from both sides. That's going to give us 2x. We're going to add 7 over to this side. It's going to give us 10. We get 2x equals 10. Divide by 2. We get x equals 5. We then plug in for RT, which is 4x minus 7. We plug in a 5 for the x. 20 minus 7 RT is equal to 13. And then we could see the other side should be equal to 13 as well. So if we go back up to RQ, we would then say, or QR, we would then plug in 5. 5 times 10, 5 times 2 is 10, plus 3 is 13. It's also equal to 13. It fits the rule. Okay, so we know that's a perpendicular bisector. We then look at example 2. We have this one's from the book on page 356. And this one is talking about, it's like a word problem. It says you have a stove, a sink, and a refrigerator in the kitchen, and you want this island. You want to put the island right in the middle. Well, how do you figure that out? Where do you put the island? Okay, so you really want the circumcenter of the triangle. So then you would figure out the bisector for this section, the bisector for this section, and the bisector. You make them perpendicular, draw the lines out. Where they meet, the circumcenter is the center of that triangle, and that's where you put the stove. And then you would measure that. Each one of these measurements, if this should be equal to this, should be equal to this, by that circumcenter theorem. That's another example. One more. Okay, so then we use angle bisectors as well. And this one says, well, what is XY? So if we know this is an angle, we know this is an angle bisector. We can see that because 41 and 41, same angle of degree on both sides. And then we also know that XW is equal to 7. We want to know what is XY. So if this is a point and this is perpendicular, then it's going to be a certain distance. We know if we draw a perpendicular line from this side, it's going to be the same. So then we say XY, right here, equals XW. And if XW is 7, XY is 7. That's that example. We then take it to another different way to look at it. And we want to know what's the measure of angle JKL. Okay, pretty easy one though. So then we have this angle here, JKM. We want to know what is JKL. It doesn't tell us what the whole angle. It does tell us though that this angle is 37. We could figure out JKM in a minute, but it also tells us that these lines right here, they're perpendicular and they're the same length. So this is meeting this angle bisector, so we know that these are the same length. They have to be. So if these are the same length, we know this is an angle bisector. So if this is 37, then angle JKL is 37 degrees as well. Then we can just go 37 plus 37. That will give us 74 degrees for the entire angle. Last one here. So we have this one. It wants to know what is the length of SP. Where's SP? Right here. Okay. SP. So, and we can tell, oh wait, this is not SP. Let's leave this T. Okay, so this is T, sorry about that. So we have S here, SP, and SM. Okay, we can see this is kind of an angle bisector, perpendicular lines, right? And then they meet here, and we would have to see that these should have some kind of indication, because we can't just look at it and say, yeah, it looks like it's kind of. We need some kind of indication that it is an angle bisector, and if these two are equal to each other, we could then say it is an angle bisector, and because of that, we can make this equal to this. So then we just do that. So SP, right here, is equal to SM, right here. So then we then plug in what they're equal to. 3x plus 5 equals 6x minus 7. We then solve it. We'll just go minus 3x from both sides. We're going to get 5 equals 3x minus 7. we're going to add 7 to both sides. 12 equals 3x divided by 3. X equals 4. Okay. So then we can plug that in. We can go 3. We want to know SP, right? So then we can just plug it in. 6 times 4 minus 7. 24 minus 7 is 23. Let's see if it's the same. So then we plug in, oh wait, made a mistake. Minus 7. 24 minus 7 is 17. Sorry about that. I don't know if you spotted that. I hope you spotted it. Then the other one is, because I kind of looked ahead and saw they're not the same answer, I better go back and check my math. And I was pretty sure I did everything. So then we go 3 times 4 plus 5. 3 times 4 is 12, plus 5 is 17. Perfect. So then we know SP is 17. We figured that out. Well, we go check it and make sure this has to be the same or we did something wrong. Kind of thought I did it first. I just didn't do my addition right. But that's that. There's several ways you can use that. I hope these make sense. These are pretty straightforward. Let me know if you have any questions. Sorry the notes are so long, but I gave you several examples in there. I wanted to make sure you understood this.